Okay.
Okay, it's good to go.
Okay, can I start?
Yeah.
Okay, so I'll start. Okay. Okay, hello everyone. So my name is Chen, and I came from the Renmin University of China, Gaoling School of Artificial Intelligence. So actually, my PhD topic is about the fairness in recommender system. So here we are. I am going to share my recent works about the equality and the distributive justice in fairness-aware recommender system. There are several works, and there are many. I will summarize their challenges and the solutions. Okay. So here I will firstly introduce some preliminary. So actually, what is fairness? So actually, fairness is about various concepts. Maybe it's about equal income, maybe it's about a proportion to labors, or we are going to take care of disadvantages. So why should we care about fairness? So actually, recommendations do not more than just reflect consumers' preference. They actually shape them. So fairness, actually, we need to give a recommended system a value or a guidance to teach what is right and to give them the social value to the recommended system. So actually, regarding to the fairness definition in the sociology, there are many concepts. So basically, there are two main definitions. So one is the equality. So equality, they are from the it is from for example in this figure. So equality means everyone starts in the same place and equally benefit from same sports, which may or may not be that case. Let me explain them. For example, if you are a man, you are born, whether you are whether is a man, you are female, you are the same, right? You are the same position. So we should not discriminate you according to your gender or your race. So this is mainly from the law's perspective. And another important view is the distributive justice. So it actually holds another assumption that everyone starts at different places. For example, I'm disabled man. Maybe I am born in nature with some disadvantaged positions. For example, I'm a disabled man, or I encounter some very terrible disasters. So actually, I need specific support and accommodation needed to produce fairness. So actually, it mainly comes from the economic perspective. So there are actually two perspectives about the fairness. So, okay, so in recommendation, actually there are multi-stakeholders. So actually in a recommendation system, there are consumers, there are the providers, and there are other stakeholders. So actually, from my group's point of view, it actually the users more related to the concept about the equality. So it actually assumes that every user starts in the same place, and we should not discriminate them according to their sensitive attributes, for example, their gender, their race, or age, and etc. And another stakeholder is the providers. But actually, we view the providers' fairness actually from the distributive justice view. So actually, it actually holds the assumption that there are weak providers, there are top providers in the market. For example, there are small providers. Maybe they just come into the market, and there are top providers. They have very strong competitions. So actually, we need to give more support to the new providers, and we not want the market to be occupied by the strong providers, right? So actually, there are two kinds of view. So here I will briefly introduce maybe 3 or 5 works, and I will introduce what can we think about them, and how can we design a solution or an algorithm to make the fairness actually happen in the recommended system. Okay. So here I will introduce the equality from the user's perspective first. So actually from the equality, it means that we should not discriminate users according to their gender, their race. Okay. So actually, first I will take an example from the large language models. So actually, here I design several prompt templates. For example, here it means, for example, you are a news or job recommender system, and we should give them a few shot or one shot, just an example. And the input is that maybe here is the example here is a browsing history of a username. Here I choose the username because the username can reflect or can infer their demographic attributes. For example, the gender, race. For example, Bob there potentially be the male, and the way potentially they are male and Asian man, Asian guy. So here I do not use the implicit attribute. For example, the male, female. It's because for example, the ChatGPT will just block the sensitive attribute. So this kind of implicit attribute, such as the username, can be more likely to reflect the discrimination patterns of the recommendation system. So here I just to use the username as the proxy variable for the sensitive attribute. So here also the browsing history there, for example, what they can maybe when he goes on a website, he browses the news, maybe five news or 10 news. It will be put in the prompt, and not based on the history, we ask the language model to rank the candidate news. Well, here we only choose 5 news for example. So we mark them as A, B, C, D, E. So we were to rank them to give them a ranking list. For example, A, B, C, D, E, the language model will output the B, E, A, D, E, right? It is actually a ranking list. So actually we will to check that if we give them same browsing history and the same candidate, but only replacing his name, or just replacing his sensitive attribute, where the large language model plays very different responses or different recommendation list. So here is our findings. So actually, we found that large language model, especially the ChatGPT, will actually exhibit very serious discriminations against certain groups. For example, in here, the news recommendation, it will give more political news to the American users, and more art news to the European users, but more education news to the Asian users. That is actually it's actually a discrimination because we give them same browsing history and the same candidate, but only replacing his names. But actually, ChatGPT will reflect different, will discriminate them according to their groups. For example, here we also draw here is the geometric features, and there is a race, there is a gender, and we can see there always exists certain serious discrimination patterns. So here we want to investigate why does such the implicit user unfairness exist. So here we conduct an experiment utilizing the probing technique. So we just utilize a simple MLP layer to predict the sensitive attribute from the usernames. And actually the answer is yes. So large language models can actually infer the sensitive attribute from users' non-sensitive attribute such as names, etc., and according to their wide world knowledge. So actually, if we just hide the sensitive attribute, for example, my female, male, they actually can infer the sensitive attribute from usernames. And we also test from the user email address. Even the email address can reflect the user's group, can reflect the user's geometric information. So here is how theories is the implicit user unfairness. And we also compare the ChatGPT with other traditional recommender models. And we found that the ChatGPT will exhibit more serious discrimination. So for example, in the news domain, it will maybe exceed nearly 80% or 100% to improve the unfairness compared to the traditional models. Actually, it will cause more serious unfairness. And in the long term, we're also conducting experiment to make the ChatGPT or the recommender system to interact the user with many rounds. And we found that from the ChatGPT, it actually will, because according to their wide world knowledge, it actually can know more users' information, and it actually can may in the future with the multi interaction with the users, and ChatGPT will make more discrimination behavior against the users compared to the traditional models. So actually, okay, so here just the analysis, and we are trying to solve this problem, but actually we are trying to figure out a solution to alleviate the discrimination patterns in the large language models. And we are going to, but we are not to give, it's not very obvious improvement, because actually large language model is very complex. So we are trying to fix that problem, but actually the problem is very serious compared to the traditional models. Okay, so here is a user side fairness, and another is a provider side fairness, and it's also related to the distributive justice. So here I will introduce the work from the three phases from the recommender system. So here is one first is the re-ranking phase. So we can all know the recommender system. There are three stages: the retrieval, ranking, and re-ranking. So I will try to model it in for three different stages, and propose different algorithm to conduct the fairness into the three stages. So okay, so here first is the re-ranking stage. So here is the paper, the PMF. So actually, here different from the user fairness. Actually, provider fairness is about to allocate actually recommended resources. For example, there are two providers. There one is this one is other one. We wanted to make them fair exposures. For example, the first providers maybe were to allocate to be exposed 10 items, and another is 100 items, and it's not fair. We want to make different providers be the items of different providers will be exposed more even, and they maybe not the absolutely equal, but actually we want to improve the worth of the providers to make not to make them more as even as much as even as possible. But actually, this paper focuses on both the re-ranking accuracy and the provider fairness. So actually, we utilize a linear combination, and the lambda here is a linear coefficient to trade off the accuracy and the fairness. So here is the algorithm. So we first design an offline solution to model it as a linear program. So I will explain it in more detail. So for example, here is GXT, it means accuracy. So here it actually to summarize all the ranking ranking scores. So the higher ranking score, I think the more accuracy will achieve. And here is the XTI. XTI, it actually means a variable. It has two possible values, 0 and 1. If 0, it means it will not into the ranking list. If 1, we will take the item into the ranking list. So actually here in the first equation, the sum xti will equals to k because we are top k ranking. For example, in the ranking list, we can only have k items. And okay, so here t, it means we totally have t users arriving in the recommended system. And the EP means the provider's exposure. So for here, we utilize the amortized exposure because we want to amortize the t equals to 1 to big T to calculate the provider exposure within the big T users. Okay. So we want to solve this linear programming, the integral linear programming. So actually, it's very, very complex and very time and actually an offline program. What we need is an online solution. So what means an online solution? It means if the user arrives in the system, he or she will only need to get the solution immediately. He can't wait others arriving in the system and can get a ranking list. And we should choose, for example, at time s, the users arrives, he will to give him or her the ranking list, and we cannot change the previous ranking list. We can only change the following users ranking list. Okay, so here we just to transfer the offline problem into use a dual problem. So actually, the dual problem of equation 1 can be written as this kind of equation. So I will not go into the detail. If you are interested, you can see my paper. But actually, when we transforming the problem into the equation 3, and we can achieve very simple computational cost. So here is our overall workflow. So actually, we just conduct the momentum gradient descent in such dual space. And here is our workflow. We firstly calculate when user arrives, we firstly to give them a recommendation, and we can conduct a dual variable gradient descent algorithm. And it is actually a very efficient process. And once we finish the computation and another user arrives, and we also can give him or her the recommendation. Okay. So here is our dual gradient descent algorithm. So here we can also bound the regret. So the gaps between the online algorithm and the offline algorithm can be bounded as such equation. So actually, it has the convergence rate about the square t. So it means the more user arrives in the system, and we can have a more accurate estimation, and we can achieve a lower errors compared to the offline solution. So actually, it's a general solution. So here is the experiment. So from the experiment, we can compare to several baselines. So here we can achieve better performance compared to existing baselines. Okay, so here is a re-ranking process. And another types of is a ranking phase. So the ranking phase and when considering the ranking phase, the different from the re-ranking stages, actually there are feedback. So actually the users will will give feedback to the data if they click, whether they click the item and or they just purchase an item. And this data are logged into the database. And the platform, the model will update their parameters according to their data. And once we get a model, and we will give the item to the users. Actually, it's actually a feedback loop in the recognition system. So here the work is, how can we achieve the provided fairness in such feedback loops of the recognition system? So here is the figure B, and we realize that actually the feedback loop will make our fairness algorithm no longer valid. For example, and here is an experiment. It means that when we increase the exposure rate, for example, the top K, the K equals to 5, equals to 10, and when we increase to the 20, and we can see the fairness performance actually increases when we increase the top K, because the feedback loop, because if we increase the exposure size, and we will expose more items will be clicked with more feedback, and we will get a more accurate the user preference. If we get accurate user preference, actually we can give them more, and our fairness algorithm can place much better. So here we want to solve this problem to the feedback loop. So actually we model it as a bandit process. So actually it also have a very intuitive example, is that if an item is less exposure, and we will give it more chance to explore. Because if we give the item more chance to explore, and we can have the more complete information about the item. Okay. So here, and when we conduct the fairness, we should we need to get a more accurate estimate about the user's preference. So here is also the algorithm. If you are interested, you can also tool down the paper. But actually, it's very general. The general conclusion is that we can also achieve a much better record bound when we consider the feedback loop. And here is a more, and it is also a more interesting conclusion, is that when we increase the T, here the n is actually the overall user numbers, and the T actually here is the batch size. So when we the batch size means when after the big T users arrives, we will update the models after the big T users arrive. So actually, the more big T becomes, and the more accurate fairness will become, but we will get a lower accuracy bound. So actually, there is a trade-off between the fairness accuracy in such feedback loop. So we need to control the batch size of the fairness of the batch size of their user size. I'm sorry, the user size. So actually, it's a very interesting conclusion. So here is also our experiment. When we consider such feedback loop, when we add the bandit process into the ranking phase, we can achieve a better performance compared to the existing baselines. So here in the long term, within the same accuracy, we can achieve better fairness, and at the same level of fairness, we can achieve a better accuracy. So actually, it actually can achieve a better it actually can Pareto dominate all the baselines. Okay. So another work is the fair set. So after introducing the ranking phase, and here another important stage is the retrieval stage. The retrieval stage is different from the ranking stage and the re-ranking stage. It actually means the items are no longer in the same server. It actually are distributed, stored in the various services. And it will also to access millions of items to select maybe 10 or 100 items. the ranking phrase also will to choose maybe 10 items from the 100 items retrieval from the millions of items. So the retrieval stage it actually require more efficiency, and it also will require our to be able to handle the distributive storage the problem. So actually we will to alleviate the fairness problem in the retrieval stage. Okay, so here we also to write an offline stage. So here we just to make the fairness constraint into a hard constraint. So here we ask every providers will have a minimum exposure of MG. So we ask every providers will have at least MG exposures of items. So here we also can write it as a dual problem. So here we just project the original space into the dual space, and after the projection is according to the dual transformation. So it actually can guarantee that they are all equal. So when we transfer the original space to the dual space, actually we can have a more better fairness estimation. So here is our online process. So actually we still can have a user embeddings, and we can connect a fairness vector or dual vector to connect to a new query vector, and the item embeddings are distributive stored in the different servers. And when we get the query vector, we can use a KNN search or a very efficient search algorithm to search in each server and to retrieve the result. And the theoretical we can show that our algorithm can very efficiently to achieve the fairness, can achieve the required minimum exposure requirement, but also can not sacrifice much computational cost. So here is our overall performance, and here is our fair stack. We can achieve. Here is 100% of fairness. So 100% means we can achieve all the 100. We can make every provider receive their desired minimum exposures. Okay, so here we can achieve 100% of the fairness, but actually we will not drop ranking accuracy, retrieval accuracy. We can still maintain a very nearly very high retrieval accuracy compared to the baseline models. Okay, so here we also can conduct the efficiency experiment. So our algorithm can maintain a small cost of inference when even if we increase the batch size, and our algorithm can achieve lower gaps between our fairness module can achieve lower additional computational costs. Okay, so here is our my conclusion is that we want to concept the fairness from two perspectives, the equality perspective and the distributive justice perspective. And those two types of fairness concepts are corresponding to the user's fairness and the provider fairness in the recommended system. And here in the provider fairness or user fairness, I'm trying to adapt fairness to three different stages: the retrieval, ranking, and the re-ranking. They have different. The three stages have different characteristics, and we need to carefully design an algorithm to keep such a characteristic of different stages. Okay, so here is my presentations. So, any questions?